Introductory circuit analysis using an unconventional, intuitive, approach. Session 2. Greetings viewers. Here we emphasize how things really work intuitively rather than blindly use mathematical methods.
In Session 1 we demonstrated how a RC circuit can be analyzed without sophisticated mathematical tools. We discussed simple stimuli like step and pulse. You are encouraged to review the material. Session 2 will start with some other types of stimuli not covered in Session 1. It will then discuss a variant of the simple RC circuit of Session 1. Let us start with a ramp stimulus. Ramp is a voltage increasing linearly with time. So, let's start with our spreadsheet. We have shown how to enter capacitance, resistance, time step, and initial voltage across capacitor, in Session 1. Therefore, they will not be repeated. Let us enter an additional parameter, namely, ramp slope A. Ramp slope expressed in volts per microseconds. We enter a value of 1 volt per microseconds. Voltage step for ramp is calculated automatically at 0.01 volts per time step in this scenario. As before, use column B for stimulus, which is ramp this time. We start ramp arbitrarily from 0.16 microseconds. Ramp voltage steps are 0.01 volts. Formulas for variables and initial conditions are same as in Session 1 and not repeated. Let's take a look at the results. After the transients have died down in about 5 time constants, the capacitor voltage is increasing linearly with time, but lagging the input stimulus by 0.65 microseconds. Under this condition, the current reaches a steady value of 0.33 mA. In Session 1, for step input, we discussed about a feedback mechanism due to KVL, that prevents charging current from staying constant and does not allow the capacitor voltage to increase linearly. So we asked the question: what if we keep increasing stimulus continuously? We find that applying a voltage ramp as stimulus, we can indeed generate a constant charging current and increase capacitor voltage linearly. Here are some expressions obtained by analytic methods, such as Laplace transform. The steady-state values of delay and voltage across resistor agree well with those from analytic methods. Small error in delay is due to finite time step. Reducing time step should reduce this error further. You are encouraged to try out the exercises shown. Triangular wave can be generated from multiple up and down ramps. We now plot voltage across resistor and capacitor to compare differentiator and integrator configurations. The capacitor has less time to charge for the faster triangular wave compared to the slower one. As a result, peak voltage across the capacitor is less for the higher frequency input. Thus integrator behaves a low-pass circuit, allowing lower frequency signals easier than higher frequency ones. On the contrary, the differentiator works the opposite way, namely as a high-pass circuit. It allows high-frequency signals more easily than low-frequency ones. We now introduce the principle of superposition by way of an example. We create a composite stimulus waveform by summation of two waveforms 1 and 2 and name the composite stimulus as 1 plus 2. Next we determine the capacitor voltage waveform corresponding to stimuli 1, 2, and 1 plus 2. We name the responses accordingly as 1, 2, and 1 plus 2. We find that response 1 plus 2 can be determined by summing response 1 and response 2. This is an illustration of principle of superposition. You can visualize superposition as follows. Consider multiple voltage sources in series creating a stimulus. Short out all voltage sources except one, and determine the response. Repeat for others similarly. Response from the individual sources can be summed to obtain the composite response from all voltage sources being present simultaneously. Superposition works for a class of networks called linear networks. The RC circuit being discussed is an example of linear network. We will discuss linearity in networks in more detail later. Superposition works for algebraic summation of stimuli, that is, addition, subtraction. It does not work for multiplication and division of stimuli. We will discuss sinusoidal excitation now. Linear networks exhibit an interesting behavior towards sinusoidal excitation. The response signal, like the stimulus, is always sinusoidal of the same frequency, but may be changed in magnitude and shifted in phase. This behavior is unique for sinusoidal excitation. As usual, column B, reserved for excitation, will contain data for sinusoid. We enter amplitude in volts. Time period in microseconds. Initial phase of sinusoid in degrees. Frequency calculated from reciprocal of time period. Formula used to generate sinusoid is shown. Phase is converted from degrees to radians. We show results for two different excitation frequencies, namely 0.400 MHz and 0.125 MHz. For the higher frequency, differentiator output is stronger. For the lower frequency, integrator output is stronger. It demonstrates high-pass characteristics of the differentiator and low-pass characteristics of the integrator. It can be then expected that at a certain frequency, integrator and differentiator outputs are same. This frequency is called 3 dB frequency as the voltage is -3 dB, that is 0.707 times the passband value. We now show the waveforms at the 3 dB frequency, at which the amplitudes of integrator and differentiator are same. This occurs at 0.2413 MHz in the present example with a time constant of 0.66 microseconds. The amplitude is close to the theoretical value of 0.707 volts, for a stimulus amplitude of 1 volt. Accuracy can be improved by reducing delta t. Steady-state behavior of linear networks, subjected to sinusoidal excitation, can therefore be completely defined in terms of magnitude and phase as a function of frequency. This is the principle behind frequency domain description of a linear network. Formulas for magnitude and phase of voltage transfer function are shown, both for differentiator and integrator. Plots for magnitude and phase are shown for differentiator and integrator. High-pass and low-pass behavior are clear from the magnitude plots. At 3 dB frequency, the voltage is 0.707 times the passband value of unity. Phase at 3 dB frequency is plus 45 degree for high pass and minus 45 degree for low pass. In the magnitude plot, points marked with a cross are ones determined from the present method, showing excellent agreement. This demonstrates the capability of the present method to determine both time and frequency domain behavior. We now point out to a limitation of frequency domain description. The limitation is with respect to transients before the circuit reaches a steady state. This is more obvious in the left-hand plot with the initial capacitor voltage not zero, compared to the right-hand one. The transient region is shown within the brown dotted rectangle. The frequency domain description ignores the transient information and describes the circuit in terms of the steady-state region only. This may be adequate for certain applications, but when information on the transients is important, we cannot use frequency domain approach. Now we discuss chirp signals, used in communication and radar. It is usually a sinusoid-like signal, but frequency is changing with time. We consider a subclass called linear chirp, where frequency is changing with time linearly. For linear chirp, the time domain expression is derived and waveform plotted. You can visualize how the frequency is changing with time while maintaining continuity in phase. Let us start with our spreadsheet. Column B for stimulus, chirp this time. Amplitude in volts. Start time period in microseconds, that is reciprocal of start frequency in megahertz. Stop time period in microseconds, that is reciprocal of stop frequency in megahertz. Chirp duration microseconds. Initial phase in degrees. Frequency slope calculated in megahertz per microseconds. Formula for chirp entered for stimulus.
Results for chirp stimulus are shown. For integrator output, expected low-pass behavior is observed. Amplitude is reducing as the chirp progresses and the instantaneous frequency is increased. Similarly, high-pass behavior is observed for differentiator output as expected. The dotted lines depict the expected envelope as calculated by frequency domain expression given earlier. We find a discrepancy between the frequency domain results and one calculated by the present method. This is due to the fact that frequency domain method cannot account for the transients. The chirp duration is not long enough for the transients to die down, and therefore the frequency domain method becomes inaccurate. By increasing chirp duration, the discrepancy can be reduced. We will discuss later the convolution method whereby this error can be reduced, irrespective of the chirp duration.
We would like to emphasize that you can use this method for any arbitrary stimulus. This includes random, noise-like signals as well. You are encouraged to create your own stimulus waveform and determine the response. Now we enter the second part of the video where we will discuss a variant of the simple RC circuit. This will add an extra branch in the network and therefore an extra variable, and this exercise will demonstrate how the present technique can handle increased complexity. Moreover, this circuit configuration is more realistic with practical implications. We add a resistor in parallel to the capacitor of the simple RC circuit. This resistor could be the input resistance of the next stage, or even the effect of an oscilloscope probe. KCL and KVL equations, used to populate the spreadsheet is shown. Let us enter the various parameters as before. Capacitance in picofarads. R1 in kilo ohms. R2 in kilo ohms. Time constant calculated by multiplying capacitance with parallel combination of R1 and R2. Next we enter the formulas for various parameters. The formulas are derived from KCL and KVL, using the same principle as in session 1 for the simple RC circuit. Immediately after the switch is closed, the voltage across the capacitor must be same as initial condition, since voltage across capacitor cannot change instantaneously. We now walk you through the various variables without audio commentary. Other formulas are same as before. Let us discuss some results now. We notice that steady state value is not the same as amplitude of the step. It is scaled by the potential divider formed by R2 and R1. The time constant is product of C and parallel combination of R1 and R2. As a result, the time constant is reduced compared to a case with no load resistor R2. You are encouraged to investigate the effect of R2 on steady-state voltage as well as the time constant. The second plot shows a pulse train as stimulus. Note how the average capacitor voltage grows with time. Now we discuss how Thevenin's theorem can be used to reduce the present circuit topology into a simple RC circuit. Once that is done, we are in a position to calculate the steady-state voltage and time constant by inspection. Therefore, we can verify if the direct spreadsheet approach agrees with the results from the Thevenin equivalent. You are also encouraged to compare the results obtained in the last spreadsheet with that obtained using another spreadsheet where the topology has been simplified using Thevenin's theorem.
This concludes the second video on RC circuits. Thanks for a patient hearing. We plan to come up with more exciting videos on other circuits. Please feel free to comment or email if you have questions, comments, or need benchmark spreadsheet files. Till then, stay safe, and stay tuned.